Hello, Honorable Math 1 students. This is Mr. Hess coming to you via my dining room, which is now my office for remote learning. You should have a very challenging set of proof problems. I think it looks something like this. Might say like 8.6 on it because I think last year I called this Unit 8. You get a few pages into there, and you're going to love these babies. These things are awesome. Courtesy of Mr. Wright. A couple of them are. So one of the things I'm going to recommend, and if we were in class, we would do this. This would be a multiple day assignment, probably 2 days we'd spend on it, one part in class and one part at home. There's sometimes you get in a proof and it's hard to explain. Something seems obvious to you and it's hard to explain it. And the rule for proofs is you have to explain every step in there. So you can't just jump in and say, well, it just makes sense to me. You got to make sure it makes sense to somebody else. So sometimes there's shortcut rules that are helpful. And on this particular packet, there's a couple problems that apply that would benefit from this new rule, which will make up. This came up from somebody in class making it up last year, actually. So the question, can we invent a rule? Absolutely. And typically you want to give a name to it, a postulate or a theorem. For lack of a better term, I'm going to call this the sum of equal parts, which in a nutshell says if you add equal parts together, the sums are going to be equal, and you go, what do you mean? Just run by a scenario here for angles or for segments in this case. If AB would be equal to CD, could you prove that AC is equal to BD? Think about that for a second. This is not on any paper I've ever given you. Jot it down if you need to. If you think about that for a minute, many of you will go, well, that's obvious. But I can tell you right now, I've taught math proofs for many years. This is not obvious to everybody. At least 50% of the American population will not find this obvious. And you might, because you're an honor student. But not even every honor student will find this obvious, I bet. Maybe I'm wrong. But I know for a fact that many, many math students do not find this obvious. Many, many people that live in America do not find this obvious. So we're going to prove it. We're going to explain why this works. Essentially, we're adding equal parts together. We know this part's equal to that part. And when you know that to get AC, you have another equal part in there. So you have that given piece of information. The other part of AC that's also a part of BD is BC. It's an overlapping part on there. If you didn't see that already, now you'll see it. So what I'm doing with this equation, I'm just adding BC to both sides. Simple, basic addition. Adding the same thing to both sides of the equation. Now I'm going to start to do some substitutions, sort of. You might look in the drawing. And again, I'm proving that this really works, so I can apply it to every other problem. So you can apply it to every other problem. The other thing you might notice about AB plus BC, if you add them together, you get AC, which is what we were after in the beginning. You'll notice the exact same thing for CD plus BC. You'd get that other one. So these are two separate ideas in my little mini proof on here. And it just so happens that this appeared earlier and this appeared earlier. So if I have this garbage equal to this trash, equal to this stuff, and this stuff is equal to that trash, it means the garbage, the trash, the stuff, and this stuff, they're all equal. There's 4 different things that are equal here. Now, just to go back, this is a little bit of Weesop. The 2 small segments add up to the whole segment, 2 small segments add up to the whole segment, and then at step 4, I can actually say these whole thing is equal to that whole thing because of the transitive property. What we just proved right here was if you have equal parts and you add them together, you get a bigger equal part. We're talking about geometric parts. I could run something like that with angles. If this angle is equal to that angle, with this whole thing equal to that whole thing, and vice versa. So feel free to use that. You're going to see this on the answer key, this sum of equal parts. Essentially, when you see this, you're recognizing 4 different things, at least 4 different things in a proof. And you go, well, this just makes sense. Instead of having to do these 4 things every single time and get very wordy and lengthy, you can sort of state that this sum is equal because these sums like this are sums that are equal because they're just adding equal parts. You still have to state the given, but then instead of writing all this stuff out in that transitive method of thinking and summing the equal parts, shortcut it. Hopefully that makes sense. Whoa. Hopefully that's helpful. Earthquake time on here. It's earth shattering. The other thing that's sort of obvious that I would go through with you if I was in class, if you have two lines that look like that and somebody goes, hey, you know what? They're perpendicular. You can say that they form equal right angles. We would go and prove this in class. I'm not going to prove it right now, but you can go and prove, of course, that all four of these angles are 90, all four of them equal. The definition of perpendicular just says there's one right angle. Of course, we can go through a process of proving that, in fact, there's four of them. I'm not going to do it now. You can see it if you want, but kind of unnecessary. You'll need this idea and at least one proof on that challenging packet. Good luck. That's thumbs up. Thumbs up.